Schiavina, he will speak about the Fritz conjecture in quantum theory.
Thank you very much. Can you hear me? Yes. So a couple of words about this project. First of all, thank you very much for the invitation. And I'm always very happy to talk about this topic because for me it was very accidental to stumble upon such an interesting question. And the history of this project is that I was listening to a talk, another postdoc, and they were talking about something completely unrelated to what I knew, what I was working on at the time. But some formulas looked very similar to other formulas that I had seen. And so we started talking, and many years later we came up with an explanation for that, which involves quantum field theory and brings it into a field that had nothing to do with quantum field theory. So what am I talking about? Fritz conjecture here refers to a statement that relates certain properties of certain dynamical systems, I will be more precise in a moment, with topological properties of the underlying manifold in which the dynamical system is framed. So in a way, we'll have dynamical systems here. And here we'll have topology, or invariance, more precisely. Okay, so Fritz conjecture is a statement that certain quantities can be related from these two worlds. They are exactly the same. And what I will tell you today is how you can think of this relation as coming from a statement in field theory. So at this stage, this is a heuristic statement in the sense that it is something we believe. I mean, it provides a heuristic explanation for why this should be true. But it also brings in new techniques that maybe are relevant to solve the issue in the first place. So you may be wondering, okay, this guy hasn't understood how boards work, but hopefully, you know, I'll manage. So the problem that people wanted to solve is how many closed geodesics are there on a Riemannian manifold. Right, so okay, this is a very vague question, but essentially this is the question that we want to answer to. And it turns out that this question makes, it's very interesting, rather than it makes sense. It is interesting, particularly interesting on hyperbolic manifolds and related. Right? In fact, it was Margulis who proved that the number, so this is the number of closed geodesics with length smaller than t has an asymptotic behavior as exponential behavior apart from this t denominator as t goes to infinity, where h and c are positive constants. So it turns out, and this is a long story that I will shorten significantly for you, it turns out that it is convenient to look at these estimates. It is convenient to look at the geodesic flow over sigma g, a Riemannian manifold. So what is the geodesic flow? So think of S g of sigma as the unit tangent bundle of sigma, and consider the map that takes a point and a unit vector and sends it to the geodesic passing through x at t equals 0 with initial velocity v, which in this case is unit norm. Okay, so this is a geodesic arc, thinking of x here. This is v, and this will be the parallel transported vector in the unit tangent bundle at gamma of t. Okay. I mean, you could work with this, but for convenience, let me introduce a slight spin on this. Since we have a metric, we can identify the sigma with its cotangent bundle. So it will be convenient for us to think about, I will define M to be the unit cotangent bundle instead of the unit tangent bundle, and because of this identification, I can think of the geodesic flow in here. Okay, so think of the co-geodesic flow. Phi of t. In the unit cotangent bundle, and denote by x the vector field generating the geodesic diffeomorphism. So there are a number of facts in this story, and the first one is that there is a one-to-one correspondence between well, closed geodesics on sigma and periodic orbits of the geodesic flow such that you can match the length of the geodesic with the period of the flow. So results on distribution of periodic orbits of the geodesic flow will be helpful to infer results on the number of closed geodesics on the manifolds. Information on geodesics. The other important statement if you want fact number 2, is that if sigma g has negative sectional curvature, then its geodesic flow, did I call it 5G? No, I called it 5T. The geodesic flow has the property of being anosov. So this means the following, that there exists a splitting of the tangent bundle, in this case of the unit cotangent bundle, such that, here there exist constants c and lambda, and for every positive time we have that so if this is at phi t of x, this is at x, and similarly, sorry, I haven't told you the most important thing yet. A moment. So this is for every W inside the stable bundle, ES. And this is analogously for the unstable. Okay, so the anosov property can be rephrased as the statement that this is minus t. Right, so one direction expands vector, the other one contracts them. So this is also like saying that the flow is hyperbolic on all M, right? So this condition for a flow invariant set is the hyperbolicity condition on that set, and this means that the whole of M is a hyperbolic invariant set, or has a hyperbolic flow. Okay. So we say, just as a terminology, that the vector field X is anosov if it generates an anosov flow. is also. Okay? There is yet another coincidence here, which is that, well, the geodesic flow on the unit cotangent bundle is also the restriction, I should say, of a Hamiltonian flow. So phi of t is Hamiltonian on t star sigma, and hence it is contact on the sphere bundle, the units cotangent bundle. So just for you, in case you want to do the calculation, it's nice. So the Hamiltonian here is just a free particle Hamiltonian, where this is g of x. Right? So if you compute the Hamiltonian flow for this Hamiltonian, you will recover the geodesic flow, and then the metric at the point x. So as a consequence, if you restrict this to m, you'll see that this is the h restricted to, well, unit vectors, which is 0, and also iota x of theta, where theta is the Liouville form, the primitive of omega, canonical structure. This will be 1. So this tells you that indeed x is also the rib vector field of theta on M, which is a contact form. Okay, so what we have concluded here is that if I have a Riemannian metric with negative sectional curvature, its geodesic flow is a contact and also flow. Okay, we'll see why this is relevant in a moment. So I said that results on distribution of closed orbits can be used to infer information on geodesics, but how do you, what are these results on the distribution of closed orbits? Well, it turns out, and I will not go into the details of this, it turns out that you can define a zeta function.
I'm sorry.
Sure.
What kind of oscillation between M and sigma?
M is the unit cotangent bundle of sigma. Yeah. Did I make?
But then it's upstairs. Oh, it's upstairs.
Right, over there.
Right.
Thank you. So Ruelle introduced a zeta function that for a flow, so well, in this case, let's say it's defined. Well, this is one equivalent formulation of it, of the geodesic flow. Where now these P of phi t denote primitive closed orbits, where by primitive I mean that have the least period. Of course, they can be multiple winding, but I'm taking those that wind only once. And L of gamma is their length or period. And lambda is complex number. So okay, before I tell you why this function makes sense, I would like to twist the construction a little bit. So what's the best color? Maybe orange? No. Let's try orange. So introduce a flat Hermitian bundle over M, and consider rho a representation of pi 1 into some, well, some unitary representation. Okay, so think of E as some d-dimensional complex vector space. Okay, we do this, then we can twist this definition in this way, and we call this the twisted, but Ruelle zeta function. One last requirement is that I want the twisted de Rham complex to be acyclic. Okay. So the highly non-trivial result is that, which is not due to me, I'm sorry, I should say that this is labeled by the representation rho. This is analytic in some region and admits meromorphic extension to C. So this is due to several people. In this particular case, for smooth Anosov flows, is due to Giulietti, Liverani, and Pollicott. But there is an alternative proof of Dyatlov and Swirsky. But this question has been phrased and answered by a number of people, which I cannot completely reference without omitting. Okay. So let's go down. Let's go down. Well, actually, yes. Not doing very well with time, but figure this out. Now, in order to define this twisted Ruelle zeta function, I needed to introduce this Hermitian bundle, and I constructed the twisted de Rham complex. So on E nabla over M, I can define the analytic torsion which I'm going to define as follows. Where this determinant denotes the zeta regularized determinant. Okay, so this is just something that I can do. And if I match E and M to be, well, the unit cotangent bundle of sigma, yeah?
So this is a certain of K, and K, what is the
Sorry?
K?
This is the Laplacian on K forms.
On K form.
Yeah, sorry. So the conjecture is that with E, M, nabla, rho as above, the value at 0 up to, well, taking the reciprocal is the analytic torsion. So this is obviously a highly non-trivial statement because, well, this guy depends on many choices. It tells us something about chaotic dynamics, so it's not obvious. In fact, this has been proven in a limited number of cases for well, hyperbolic manifolds of constant negative curvature by Fried himself. And then it was, so this is Fried. And then was later generalized to low-dimensional cases of non-constant negative curvature by Tang, Yarmo, Rivière, and Shen. Who also gave a proof for certain homogeneous spaces, sorry. But in general, it's pretty much open. So, well, let's see what we can say about it.
So what's the role of rho in your torsion?
Here? Well, I mean, it's one-to-one with the flat I mean, it's related to the flat connection. So you take the flat connection gives you holonomy. Okay, so this is a conference on DG manifolds, so I haven't said anything about that. But I will now. So where does field theory enter the game? This will be my connection to DG manifolds. So now for something completely different, let's talk about field theory briefly. Okay. So in field theory, we want to make sense of this quantity for starters. Okay, so we have some space, fields, and we want to make sense of this. Okay, where F is some space of fields. I don't want to be too general here because I will look at a concrete example. So just to have an idea of what's happening, S is some local functional, but also not necessarily. And d phi is supposed to be some measure on this space which doesn't exist in most cases, or we don't know if it exists. So this integral is, as David says, it's a cartoon. Right? So the way one can attempt to make sense of this is by formal power series in H bar, which leads to the calculation of Feynman diagrams as the coefficients of this power series in H bar. But there is a problem whenever I'm talking about a theory that has a local symmetry. So if I have local symmetry and this denotes my F, I will have, let's say, orbits of a gauge group acting on it. Well, because of the symmetry, the Hessian, which is sort of the necessary ingredient to construct these Feynman amplitude diagrams, will be degenerate. So the critical, in other words, the critical points of this action functional will not be isolated because of these orbits. So roughly speaking, what we want to do is slice these orbits so that they are counted a finite number of times as a presentation of the quotient. Okay, so we want to present the quotient F over G, and one way to do it is by coming up with a clever way to construct a slice, a image of this quotient map. This choice is called gauge fixing. And the moral point is that we want the quantities that we extract from our theory to be physical, and so they shouldn't depend on the choice that we make to extract them. So one way to treat this problem cohomologically is the Batalin Vilkovisky formalism. And I am really out of time, but okay. So we have seen, luckily, a bit of this in the previous days, so I can maybe go a little faster here. So what we want to assign to this problem is some -1 symplectic space. Okay, let's not even bother. It's a vector space with a -1 symplectic pairing. And I want a function of degree 0 that satisfies the classical master equation, which is a statement that S bracketed with itself is 0. Additionally, and let's say that here we're working in finite dimensions because I want to actually state a theorem. Let's say that we are additionally equipped with a Berezinian on this odd symplectic manifold, and I denote by delta mu its associated BV Laplacian, okay, which is an object that squares to 0, and, well, on functions, it's defined as the divergence with respect to mu of the Hamiltonian vector field of a function f with respect to the symplectic form omega. So the point I want to make, I don't want to go too much into the details of field theory, but the point I want to make is that to make sure that this choice is immaterial, I use this result that says, this is Batalin Vilkovisky. So for every f, g, and h, such that f is delta mu closed and g is delta mu exact, I have the following. For every Lagrangian submanifold inside this -1 symplectic space, the integral over L of a delta exact function is 0. And for every smooth family of Lagrangians, I have that the time derivative of the integral over the Lagrangian submanifold of f, which is delta closed, is 0. So this tells us that at least in finite dimensions, it makes sense to consider Lagrangians as a good way to extract, to enforce this gauge fixing condition. Okay, I'm not being too explicit about why these two things are related, but yeah, I can ask questions. Okay, so for us, given a field theory, I can input it in this Batalin Vilkovisky formalism, and I think that there should be some generalization to infinite dimensions of this theorem, that choosing smooth families of Lagrangian gauge fixing conditions should not matter, right? The actual choice within that family should not matter.
So, shouldn't F and H be compactly supported for this?
Right, yes, sure.
So could that be relevant to the application later?
I mean, I'm always thinking that, maybe I haven't said it, thank you for that, that sigma is compact, right? So I'm always, no. I think the problem is that we don't really have a framework to state this in infinite dimensions. I mean, what's a Berezinian? You don't know. But okay, something can be done maybe. So this goes down. Nope. This goes up. This goes down. Okay. I'm really sorry. I think I will just get to the maybe to the statement, but all right. Okay. So what is the theory that we're looking at for this particular application? This is BF theory, in fact, twisted and abelian. Okay, so we have seen BF theory in Owen's talk yesterday, but let me fix the notation. So again, I'm thinking of M being the unit sphere bundle with E on top. And the infinite dimensional space that I'm looking at is just given by two copies of differential forms, but I need to shift them in degree because of BV, where n is the dimension of M. And I have a symplectic form, which is just given by this, where it's just a note of vertical derivative, sorry, differential over the space of fields. And yes, the action functional is just the top form part of BdA, where D is the twisted de Rham differential that we had before. So in this setting, a gauge fixing is a Lagrangian in the sense of an isotropic subspace with isotropic complement. So for me, I have a gauge fixing in this case if I can find a splitting into K plus L. This can be generalized, but for now, let me stick to that. And in particular, I want both L and K to be in the image of some operator which goes from F to F, and squares to 0. Okay, you will see in a moment that this makes sense in the examples that we're interested in. Same for K is going to be the image of some operator QGF perp with similar properties. And let me define D as the commutator of this gauge fixing operator with the de Rham differential. I call this the characteristic operator given the gauge fixing. Okay, well, the moral of the story here is that if you take this theory, there are two valid gauge fixing options. So the first one is called Lorentz gauge, and it's the choice of the codifferential as gauge fixing operator, which means that L is given by coexact forms. Okay, notice that here, since QGF goes from F to F, I should actually say this, but okay. This is given by coexact forms. And QPerp, in this case, is just a copy of the twisted de Rham again. But there is another choice, which I call contact gauge, which is given by, oops, sorry. Two copies of the contraction operator with the Anosov contact vector field. Okay, so this, if you want, the statement is that this guy is Lagrangian in FBF. Okay. And here's the, well, let me say it as a overall statement. So this is a series of people starting from Schwartz, and then and myself. Well, if you compute the partition function of BF theory using this Lorentz gauge, you get the analytic torsion. And if you compute the partition function of PF theory in this contact gauge, you get the value at 0 of the Ruelle zeta function. So, okay, just to conclude, in the dynamical systems, we can compute the Ruelle zeta function and then exponentiate it to some power. Here we can compute the analytic torsion. Well, field theory relates this to the partition function with respect to a particular gauge fixing choice. So the question is now, can we use this link to prove that that the partition function, in other words, is locally constant on choices of Lagrangian submanifolds? And do I have 1 minute? Thank you. So we're not quite there yet, but we have this result. Under some regularity assumption, we can prove that if I have a family of gauge fixing operators of a certain type, unfortunately I don't have time to go into the details, and I define again, the characteristic operator as the commutator with the gauge fixing operator and D, well, this object is locally constant. As a corollary, we are able to apply this framework. So using the structure that is imported by field theory, we can deduce the statement that, well, the analytic torsion seen as the superdeterminant of D star G, D, where G depends on T now, restricted to coexact forms, maybe to some power, I think I need to put 1/2, is locally constant. On what? On curves of metrics. Okay, this is Ray and Singer, but reproved in this way. And independently, the value at 0 of the Ruelle zeta function, which is the superdeterminant with some regularization of this guy, probably in this case, because I'm using just that as this, is also locally constant. And so this was also proven by the GRS, people I mentioned before that I have erased. So we get an alternative proof of that, again, using field theory. The question is there a Lagrangian homotopy between d star g for some g and iota x for some x. If so, and if you can prove that this Lagrangian homotopy satisfies these regularity assumptions, which are analytical in nature, then you prove the result. Thank you.